Assalamualaikum and welcome back to our example 2 and 3. As per last lecture, we found our structure stiffness metric. Now we're going to find force in each members. To our example 2 and 3. As per last lecture, we found our structure stiffness metric. Now we're going to find force in each members. Structure stiffness metric. Now we're going to find force in each members. Refresh back to your note. We know our stiffness is K equal to AE divided by L. Then by assembling structure stiffness metric, we are possible to find forces and also displacement at each node. Now, refer back our last lecture. We numbering our nodes member near and far direction. Remember, we have to number our unknown displacement first. Also, you have to look what the external forces applied and also support at each node given to you. This is the formula for member stiffness, and when we assemble for each member stiffness, we're going to combine together and finally we get capital K. Small k is for member. For this question we have K1 and K2. We combine it together for structure stiffness metric, we get capital K. Refer back to this formula. We're going to use Q for our F. At each node, we know there will be forces, and also at each node there will be displacement. So we can summarize that as Q equal to KD. So this for our total system. This is Q, this is K, this is D. For this system, we can divide into unknown and known. As mentioned last time, in the last slide, unknown is those displacement we don't know, and known is those displacement we know. For example, at our support here, displacement is known, which is 0. Displacement at 3, 4, 5, and 6 is 0, definitely. So with this, we're going to categorize our metric into group of unknown, group of known. By knowing boundary between known and unknown here, we're going to construct a line between known and unknown, as you can see here. Together here, force known and force unknown. With this metric known and unknown, we can extend that, and finally we're going to have two main equation. Equation 1, equation 2. Definitely here for D known is 0. Then from here we can get force known is K11 times du plus 0, or because here is 0, We write K11, du is QK. Same for QU. We will get K21 times du plus 0 because d known is 0, and our QU we can write K21 times du. Back to our question. Previously we already developed our structure stiffness matrix, which is as we can see here. Now we're going to assemble our structure stiffness matrix into complete force displacement equation, which is Q equal to KT. This is force displacement equation. This one will be our Q. K, capital K, is our structure stiffness matrix, and this one is our D, displacement. Refer back to our question. We know we have support at point 1 or joint 1 and support at joint 3. Due to support condition, due to this support condition, we know at direction 3, direction 4, direction 5, and direction 6 is 0, where displacement at 3, displacement at 4, 5, displacement at 5, and displacement at 6 equal to 0. At joint 2, there is downward force, where force at joint 2 is, we can name as F2 equal to -2 because downward, and there is no force on direction 1, which is direction X. Therefore F1 equal to 0. So we're going to put those known and unknown. Therefore we're going to include known displacement and also known forces at that particular directions in our system. Back to our structure force displacement matrix. We know by our numbering for our matrix, where this will be displacement at direction 1, displacement direction 2, D3, D4, D5, and D6. This is force at 1, force at 2, 3, 4, 5, and 6. As we defined here early on, we know D3, 4, 5, and 6 equal to 0. Therefore, this is 0. 0, 0, 0, 0. Then we know here is the boundary between known and unknown. So draw line between known and unknown. So we construct horizontal line for unknown and known. Now we need to find this boundary on our structure stiffness matrix. To find the boundary, we count from our Q 1, 2. So we count on our K 1, 2. Then we can draw the vertical boundary in our structure stiffness matrix. So this is our vertical boundary on our structure stiffness matrix. Also, we know our forces at joint, where force at 2 and 1 is 2 and 0 respectively. Sorry for this mistake. We are using Q for the naming. So this one Q2, this one is Q1. So we have to put this info in our matrix. Q1 is 0. Q2 is -2. Now we done assemble force displacement for our structure system, where we know where is unknown forces, known forces, known displacement and unknown displacement into the shape. And also we got to know what is this boundary for our metric system. Then we can extend into two main equation, equation 1, equation 2. From equation 1 we can find displacement, and from equation 2 we can find forces. For For question 1, we can get displacement. Refer back our main matrix. This is equation for this is metric to find our displacement, where we know this is the metric system to find our displacement. K11 this is our K11 times by du. This is our du, which is unknown. So we have to assemble that into new form to find our displacement. So here is 0, -2. Our K11 0, here is 0.405, 0.096, 0.096, 0.128. And for our D unknown is D1 and D2. D1 and D2. And we know our dk is 0, so both is 0. At this stage, we should able to do metric operation Here's some tips how to do matrix operation. For example, we're going to take K12 times dk. This is our K12 times by dk. This is our dk matrix. Matrix size for K12 is 2 times 4, and for matrix size dk is 4 times 1. Remember, for matrix size, always row times column. So for this matrix operation, we're going to get matrix size of 2 times 1 as a result. Always remember, if you're going to combine or multiple two matrix, always must have same column number times by same row number. Then the matrix size for the result of K12 times dk is 2 times 1. Therefore, size at here is 2 times 1 size. Size for this one is 2 times 1 matrix size. Now we're going to extend this matrix, then we will get two equations with two unknown. For the first one, 0 equal to AE times by 0.405, 0.405 times by D1 plus 0.96 times D2 plus 0. First equation. And for the second equation, negative 2 equal to AE 0.096 D1 plus 0.128 times by D2 plus 0. Second equation. Now we have two equations and two unknown, then we are possible to get what is D1 and what is D2. D1 is 4.505 divide AE, and D2 is negative 19.003 divide AE. Negative sign to indicate downward displacement, while it here is positive, so this one to the right side or rightward displacement. As we know, at each point we have x and y, where upward is positive, rightward is positive. The unit for our displacement is meter, don't forget that. For the second equation, we will get forces. Refer back our main matrix. This is for second equation. With the boundary we identified early on, we know where is K21, where is DU, and where is K22 and dk. Assemble that matrix for second equation. We know our dk is 0. Certainly here is 0. Remember the matrix operation. Transfer those values from main matrix here into here, Q3, Q4, Q5, Q6. Here is 0.033, 0.072, negative 0.096, negative 0.096, negative 0.128. We already know what's the unknown in here, D1 and D2. D1 is 4.505 AE and D2 is negative 19003 AE. To make easier for us, take out AE value, become 1 over AE. As we can see here, we can cancel out AE value. Then we have to expand this matrix. For the first one, when we solve, we're going to have Q3 equal to negative 0.0333 times 4.505 plus 0. Then we will have negative 1.5 kilonewton. Then for Q4, do the same. Expand the matrix. We have answer for that, 0 kilonewton. Q5, negative 0.07 times by 5.505, negative 0.072 times 5.505 plus negative 0.09 0.096 times by negative 19.003. Then we will get 1.5 kilonewton. For Q6, we get 2.0 kilonewton. Please check summation F y direction is 0. That means that in equilibrium. And those answer you get from Q3, Q4, Q5, Q6 is correct. Now we're going to find the internal forces in our members, member 1 and member 2, by using this formula. From here, please remember Q near equal to negative QF. Bear in mind, for member 1, for near X, near Y, and for X, for Y is 1, 2, 3, 4, while for member 2, this refer to X and Y displacement on each member. For member 2, near X is 1, near Y is 2, for X is 5, and for X is 5, for Y is 6. For member 1, length is 3 meter, lambda X is 1, lambda Y is 0. So by using formula for QF, Q1 equal to AA divided 3, negative 1, 0, 1, 0 times by D1, D2, D3, and D4. D1 is 4.505. D2 is negative 19.003. D3 is 0. D4 is 0. You have to do matrix operation in here. For this one is size of 1 times 4, and this one is 4 times 1, so we will get matrix size of 1 times 1. Expand your matrix, we will have value Q1 negative 1.5 kilonewton. Do the same for member 2. Length is 5 meter. Lambda x is 0.6. Lambda y is 0.8. So Q2 AE divided by 5. Using QF formula, negative 0.6, negative 0.8, 0.6, 0.8 times by displacement at 1, 4.505. Displacement at 2 is negative 19.003. D5 is 0. D6 is 0. Expand this matrix, we will have Q2. Therefore, we find what is force in our members. Also, force at node